Oxford University, which will speak about two loop integrands from the Riemann sphere.
Well, let me first of all say thank you again so much to the organizers of the conference. Stockholm is always a great place to be. And as you've heard already, I'm going to give a continuation of the last talk. So I'm going to tell you how everything that you've heard about just now can extend to two loops. So just to review very briefly, this is a story you all know very well about. Obviously, it's not a good approach to amplitudes to start from a Feynman diagram expansion, because we know that the graph combinatorics get untractable, even for a very low number of points. And just to contrast this, we know that in string theory or in other worldsheet models, what we get instead is an expansion in the genus of the underlying Riemann surface. So, in particular, we get one unique object at every genus. Now, the payoff for this is obviously that we have an integration over the modular space, so we have an intrinsic geometric problem. And our quantum field theory we recover as we take the appropriate field theory limit of the string theory. Now, what Ricardo has introduced you to are the CHY formula, and as you've heard there, they have a very natural origin in terms of ambitwisted strings, which is a worldsheet model that maps you to ambitwist the space of null geodesics as a target space. And this has the remarkable property that it reformulates Q of t in the same expansion over worldsheets of different genus, but it has the remarkably, it localizes the moduli integral completely on what are known as the scattering equations. So the reason why we like these formulas so much is that this is an algebraic problem, and in general, we just know very much better how to solve algebraic problems. Now, Ricardo told you how to go from a genus 1 torus to a nodal Riemann sphere. So I'm always going to denote that by two additional points that are identified. Now, we know obviously that there's a lot of remarkable progress at one loop that doesn't necessarily extend to two loops. So what I'm going to try to convince you is that this is actually something very intrinsic, and that's something that tells us something more about quantum field theory, that this actually extends to higher genus. Okay, before I go there, let me just very briefly review what happens at tree level and at one loop. So, at tree level, the best version of formulating the scattering equation, or the most compact one, is to construct a one form P of sigma on the Riemann surface, or Riemann sphere in this case, if I'm at tree level, that identifies, or that uniquely associates to each marked point sigma I, a particle ki by taking the residue. So we're constructing this P sigma as a sum of a ki sigma minus sigma I, and then the scattering equations will always have the geometric interpretation that they enforce that P squared, the quadratic meromorphic differential, is 0 everywhere on the Riemann surface. Now, the easiest way to do this is just require that all residues of P square vanish. This is sufficient as long as we're on the Riemann surface. And what we get are exactly the sum over j, ki dot kj sigma I minus sigma j, which are the scattering equations that you've just been introduced to. Now let me just make two very short comments, because these are two of the main properties that we will use throughout. Now, remarkably, these scattering equations, the reason why they're called scattering equations is that they know intrinsically about scattering amplitudes in the following sense. If I have some of these points going together, which is equivalent to a Riemann sphere with some of the marked points bumping off, and these degeneration limits correspond to factorization channels of the amplitude. So in other words, these scattering equations know about all possible poles that the amplitude can develop. Now the other point that will be useful throughout, although I'm not going to say very much about it, is that these have an origin in terms of ambitwisted strings. Now Ricardo told you a bit more about this. The only fact that I want to use, everything else you'll have to take as given, considering the time, is that ambitwisted strings tells us to construct a P as a solution to this equation. D bar P is 2 pi I, sum of ki, then localized in sigma minus sigma I. You've seen briefly from Ricardo that this came out of Welsh correlators with the corresponding vertex operators, but we will just use this final expression. Now, as I've pointed out, the tree-level S matrix completely localizes on these, and as you've seen, I haven't made any comment about what theories I'm talking about. The only requirement right now is that these are massless theories with some nice properties, because there are actually quite a variety of integrands that you can compute. So in some sense, the scattering equations are universal, and only the integrand will tell us what theory we're dealing with. Now, the ones that I'm going to be interested in are, in particular, gravity and Young-Mills. I've included the Geyer scalar for completeness. I've tried to color-code a bit the color kinematics duality. So you can see very nicely that for gravity, we take two copies of what you could call a spin 1. Which basically, the only thing you need to know is that this is a completely well-defined matrix in terms of the momenta, the polarization data, and the marked points. And to get to Young-Mills theory, we just replace one of these by a Park-Taylor factor, which encodes the color, and the Geyer scalar is given by just two copies of the color. Now, you might have seen that I've done there a sort of unconventional going down from gravity to Young-Mills, but you'll see that this will repeat, because in this case, actually, the theory that we understand best is the gravitational one. Okay, so now what happens at loops? You've seen that if you take a Welsh correlator, you can expand it on the genus 1 and see that what you find is this one loop amplitude. Note that we have to integrate, in addition to the usual insertion points, the modular space now includes complex structure, so we integrate over d tau. But it has the same remarkable property that everything is completely localized, up to here, sorry. The integrand is completely localized on the scattering equations, and the integrand itself is just given by some of our spin structures. Ricardo's shown you in a bit more detail what this actually looks like. So, as I've told you, so we're just solving this equation now on the torus instead of the Riemann sphere, and what we find is, well, we find a factor that looks very familiar, except for that we have here the corresponding propagator on the torus, versus up here we have a new term, which has, if you want, the zero modes of p, and we've encoded them in this, what I've conveniently called L. So you can see that already from here it's very suggestive that we can give this the interpretation of a loop momentum. The scattering equations are just as before. They're enforcing p squared equals 0. Again, we're doing this by setting all the residues to 0, and minus one of these are independent. But you can see already that due to this to this factor here that is completely holomorphic and global holomorphic, then we get actually, by setting to 0, we don't enforce p squared equals 0 yet, we just enforce that p squared is a constant. So there is a last equation that sets p squared at any point to 0 to enforce that this constant is actually vanishing. Now, the two key properties, none of the other details are very relevant, is that this is actually modular invariant. So if we scale tau to tau plus 1 or tau to minus 1 over tau, the whole formula with appropriate rescalings of the other variables is invariant. And as I've pointed out, this is completely localized. So what we can do then is, on the support of these other equations, we're just left with an integral over d tau that is completely localized. And for this integral, so these are the solutions to this, we can now apply contour deformation. So instead of integrating around all of these, we can swap the contour around, integrate around the boundary of the fundamental domain. Now, since everything is modular invariant, sides cancel, the contributions from the unit circle cancel, we're just localizing when tau equals I infinity. Now, you can see beautifully, so down here we have a nice fat torus, and up here this completely degenerates, so we're completely pinching an A cycle, and what we're landing on is exactly this null Riemann sphere with 2 points that just by convention are called sigma plus and sigma minus, because it has the nice interpretation of the loop momentum flowing through with plus and minus. Now, under a nice change of variables, you can see that this now gives us a new p. Remember, before we had this L dz plus Ki with the propagator on the torus. Now, the propagator on the torus naturally degenerates to the Ki over sigma minus sigma I that we know and love. And the other terms degenerates into an L over sigma minus sigma plus minus L over sigma minus sigma minus. You can see that this has a very nice interpretation in terms of a forward limit. So you could have equally arrived from that. In fact, Alice, Song, and Freddie arrived at this from that angle. Now, the most convenient way to write down the scattering equation is now to define S. Now, you notice that this is basically just p squared, but I've removed all the double poles, so that I can conveniently now say that I'm again setting to 0 all the residues of this S, and these are the scattering equations that you get from this. Now, again, we said we're now completely localized again, and the formula that we get has now remarkably just the complexity of an n+2 particle tree-level amplitude. So this has a similar complexity. It is therefore something that we know very well how to deal with. Okay, again, just to briefly remind you, the integrand, we can play the same games. This is the one that we get from the Bellevue correlator, where we basically just have two copies with a nice sum over Pfaffians. But we know, or well, you can conjecture and then prove afterwards that you can again use color kinematics to get to super Yang-Mills, where you just insert a Park-Taylor factor here. Now, with these two fundamental building blocks, you can then describe, you can also go to other non-supersymmetric theories, and checks that we have done on this are both numerical and factorization. Okay, so far the story up to one loop. Now, obviously, the big question is, can we go beyond this? So, a lot of examples like the finite tree theorem, especially since this has an interpretation of forward limits, you might be worried that this might actually stop here. So, it is a crucial check to prove that it extends beyond this. Okay, so let me give you some heuristics, basically the most elementary building blocks of how this is going to work. So let's start from any Riemann surface sigma g. I know this looks as though I've jumped to 3 loops, but because this is completely general, this is just meant to emphasize that this works in principle, everything I'm telling you here for any genus. Now, we can apply residue theorems as long as our measure over the moduli space has appropriate poles, and contract the A cycles everywhere to land down on a nodal Riemann sphere. So you know, over here we have 3g minus 3 moduli plus the n for the marked points. Now this procedure fixes g of them, so we're left with 2g minus 3 moduli. Now you see, number magic, this all works out. The 2g minus 3 is exactly the 2g marked points, new marked points that we get from these double points here, modulo the SL2C invariance on the sphere. Beautiful. So what happens to the one from P? Well, we know that P is always expressed as some zero modes LR omega R, but this is a basis of global holomorphic one forms, first on the Riemann surface of higher genus, but once we degenerate, we actually naturally pick up these forms that have poles at exactly the 2 marked points. Okay, so much for the general setup. These are all the basic ingredients. What does this actually look like for 2 loops? Now, we can rely on some work by Tim Adamo and Eduardo Casali, who've worked this out from the pure spinor perspective and found the following expression. So I've condensed everything that we can factor out, so a lot of kinematic prefactors in this n. This naturally contains a T8, T8 out to the 4. And then we have an integral over the moduli space now at genus 2 with 4 marked points, 4-point amplitude. We're integrating over the period matrix where we've defined the period matrix in the usual way. Now mapping mu is again what I've written on the last slide. And we get a localization on these new scattering equations. Now you see this is a natural generalization of what we had before. We're just setting all the residues at all the marked points to 0. That enforces that p square is global and holomorphic, but since we have 2 different 0 modes, L1 and L2 now, there's actually three constants left that we still have to set to 0, which is what this last delta functions are doing. I've written this in the most invariant way, where I'm pairing a Beltrami differential mu with a p-square form. Now, the usual choice is that, or in the literature, the usual choice is that you just set p-square at some arbitrary marked points to 0. This is what we've done at one loop. But a more invariant choice that you could pick is that you expand p-square on the support of the other scattering equations. This is global and holomorphic. So you expand it in coefficients of the basis of holomorphic one forms, WR, WS. And then you just set to 0 these coefficients. Okay, last ingredient that I have to tell you, the integrand is just something nice and short and well-defined. You just get some kinematic prefactor, k1 minus k2 dot k3 minus k4 times 2 deltas, where the deltas are just defined as antisymmetrized products of these omegas, plus permutations. Okay, so if we now want to apply the degeneration that I've told you about, let me just go back one. What we want to do is start integrating by parts on these two delta functions, on two of these delta functions, to localize on the boundary of the moduli space. Note that we just have two, so we just want to contract two A cycles, so we'll still be left with one. Now there's very nicely unique boundary that you land on in terms of the, so you strip off, once you degenerate, you notice that the prefactors of the omega 1 square term becomes L1 square. So in particular, if you want to keep your loop momentum general, you'll have to degenerate that delta function. So that means that you're landing on something very nice, so I've already degenerated it. As at one loop, we're picking up a prefactor of L1 square and L2 square, and we have the same integration over the marked points, now over all marked points modulo SL2C. And the scattering equation set to 0 the residues at the marked points, where I've defined my S conveniently just as before as p square minus LR omega r, all squared. Now, this looks very nice and neat. The problem is that I've forgot to tell you something here, which is the following. Remember that we had a mu here, which I basically told you could pick anything here. So in particular, who told us that you should pick U11, U22, and U12 here, and not some linear combination? In fact, this option for a linear combination will make itself manifest here in giving us a term that I've just included now with an arbitrary constant, A12, times L1 square plus L2 square, omega 1, omega 2. So remember, so we've integrated by parts on two of these delta functions. So this is basically just the freedom to add their arguments to the last delta function. Or in other words, A12 just corresponds to different choices of mu. Now this is a crucial term. Why? If I write out the scattering equations, you see that this introduces an L1 squared, L2 squared, the scattering equations themselves. Which means that for the first time, the scattering equations now can depend on L1 squared and L2 squared. So it makes a crucial difference of whether this is in there or not. Obviously, the crucial question now is how do we fix this constant? Which is still unclear actually from the ambitwistor string, so there's a lot more work to be done there. If you want to have my guess, there is modular invariance properties. If you make those manifest, that should uniquely fix that, but that is definitely still work in progress. What you can do instead is just take a physicist's approach and say, okay, what properties do we need to fix this? And obviously, the answer is factorization. So let me just very briefly tell you, I've told you before that the scattering equations have the remarkable properties of relating factorization channels of M to degenerations of the nodal Riemann sphere. In particular, at one loop, there are two cases of interest. So let's just do briefly one loop to see how this works. So there's a separating one where just sort of a bit bubbles off. That gives us the usual factorization channels. There's something that is known as Q-cut degeneration worked out by the Copenhagen group, where this degenerates into something like this. They give you two different poles. Pole structure for the separating case, very nicely just the Ki squared. This is what you expect. But you see that for the Q-cut case, you actually get these linear poles in L, which are a typical feature of these shifted integrands that Ricardo introduced you to. Okay, so at this point you should definitely have the question, why these poles, and so why do we get them, and why are they the correct ones? Why do we get them? Now, the P has the very nice property that it splits naturally when the Riemann surface degenerates. So it splits into a bit. It comes with a pole that lives on one of the degenerate ones and one that lives on the other ones. So then it's just an algebraic property. You can check this by just calculating that this property as tilde I, that is just the sum over ki dot kj with a factor of 1/2. This is an algebraic identity. And, well, this is just with this definition of pi, some linear combination of the ki dot pi. So the scattering equations on the degenerate one. So this vanishes. So this tells you, with a bit more work, that this is exactly the pole that is flowing through this cut here. Okay, that tells you why you get the linear poles. The reason why these are actually the ones that you want is the following. This is completely separate, so now I want to start from, if you want to find a diagram-like expansion, with a numerator that can depend on L, and some denominators that all depend on L. So everything that does not depend on L and might or might not sit in the denominators, I'm still putting in this numerator factor. Now the way to get to the Q-cuts is the following. Shift the loop momentum by something that in general will live in higher dimensions, because I want that dotting this vector eta with L and Ki gives me 0. But this eta square is some constant that I'll rename Z. Now, just by definition of these propagators, it shifts all of them to a factor of Z. So what we can do then is apply a Cauchy residue theorem that shifts us around, wraps the contour around, so then we get exactly the sum over shifted integrands that Ricardo was showing you. And by shifting L by an appropriate amount in each term, we can factor out a 1 over L squared in front. Now, if we do a further rescaling to remove all forward limit singularities, we land on a nice expansion that tells us that the one loop amplitude is splitting into two three-level amplitudes with shifted loop momenta that are now manifestly on shell, and these shifted ones over 1 over L squared 2L dot Ki plus Ki squared. Beautiful. So these are exactly the factors that we get. This is actually how you prove the one-loop formulas. Now, what happens at two loops? Now, at two loops, if you go through exactly the same procedure, what you find is that there is a term, this is the term of interest, there's another term present in non-supersymmetric theories, where here we have two tree-level ones, but now it's over L1 square, L2 square, and another term that's quadratic. So you see that if we had set naively the A12 to 0, this would have definitely given us not the correct answer. Okay, so to make this explicit, now let's look at this degeneration. This is exactly the degeneration that will correspond to the Q-cut that we're interested in. If we calculate the pole, well, we get this A12 L1 square plus L2 square plus these other terms. And if we require this to be L1 plus L2 plus Ki all square, then this fixes us with A12 equals 1. So we've used the factorization properties effectively to find what this is. Just two brief comments. Now, obviously, as they have to be, the resulting scattering equations with A12 equals 1 are Möbius invariant. So these are SO2C invariant as they have to be on the Noether Riemann sphere. Now, the only other thing is, these scattering equations, I told you before, they know about all potential poles. And in fact, they seem to know about a pole that you don't want here. So they know about a pole that looks like minus L1 plus L2 square plus 2L1 minus L2 dot Ki plus Ki square, which looks really bad. This is not a problem as long as this never appears in the integrands. So this effectively gives you a selection criteria for what integrands you can write down. Okay, so finally, we've put in all the work. We localize on the scattering equations that we've just now worked out. We've put the constant here to 1, so this is all, we know all of this now. We've essentially checked factorization properties already, because that's how we derived them. There's a bit more work to prove that you have to get the correct residues as well. So the only other thing I have to tell you is the integrand. And obviously the nice point is that for supergravity, we can just take the correlator and check and just calculate what it is in the degeneration limit. Now we get a beautiful y over j squared. Here y is exactly the same factor that I told you about before. And this is basically just a Jacobian that comes from the coordinate transformation that we've done to cut down to the Riemann sphere. Now you see there's another factor sitting in here. What this factor does is it removes exactly the unphysical poles that we don't want. Note that I should comment on the fact that it's not clear yet how this arises from the ambitwistor string. However, it is very clear that it gives us the correct amplitudes, both the planar and the non-planar ones. Now we can use color kinematics to land on super Young-Mills. Again, there is no ambitwistor string for this, so this is just working by the usual color kinematics duality. Substitute one of them by Park-Taylor, where this is an analogy of what we have in one loop, with now all points involved for both loop momenta. And this is the one that you use for the planar one. And we've checked all of this both numerically and from a factorization point of view. So now let me just wrap up. So what we've done is we've checked that this formalism extends actually to two loop integrands for supergravity and super Young-Mills. And on the way we found actually a genuinely new property that the new scattering equations have. Now, the derivation that we had was crucially relying on the fact that we had something to start from, so the ambitwistor string origin that gave us the first integrand, that we were completely localized in the scattering equations, at least for the integrand, that made it possible for us to wrap around the contour and land on the nodal Riemann sphere. We have used over and over again the color kinematics duality. You can really see how strong this is and how much this allows us to do from the fact that we've moved from, that we got Young-Mills out for which there exists no well-defined ambitwistor string, to higher genus at least. And, well, for the proof, we've used the factorization properties of the scattering equations. So my summary is this extends definitely to two loops, and you can see a pattern in how this would work for higher genus. Now, just as a brief outlook, obviously I've highlighted one of the open questions already, so there's some work to do to sharpen the derivation from the ambitwistor string and to make this more manifest. What is obviously interesting is how this works for non-supersymmetric theories. There has been some work done already from a slightly different angle by Lofang. There is something definitely that can be said, but there are still a few numerical checks outstanding. So NS Young-Mills actually and bi-joint scalar we do believe work. And obviously always the question, what can we do at higher loops? Thank you so much.
We have time for a few questions.
Can we go back to the formula for the Young-Mills, please? Even the previous one.
Oh, sorry, yes.
So I saw this last line when you show this formula for I2, the calculator. And I guess in the summation, the factors like sigma, sorry.
Yeah, okay,
So I just want to say something about my worry. So do you have some factors like sigma of 1 plus 1 minus together, something like that in the end?
No, so you see that on the other side, this y has factors of sigma 1 plus 1 minus 2 plus 2 minus in the numerator. It actually squares. So and there are never any poles. That is absolutely crucial. There are never any poles overall in the sigma 1 plus 1 minus and 2 plus 2 minus, which is absolutely crucial because these correspond to, if you want, tadpole contributions. So these are always there. Even if it doesn't scale with it, you have to worry about degenerate solutions, and these are crucial to exactly the non-physical poles that you found.
Yes.
So these never appear.
Okay, good.
They're always suppressed. Maybe to expand on that just a second. So you get the worry was that at one loop there are potential non-physical poles that you have to worry about. And these correspond to, if you want, degenerate limits, where just in the factorization, just the two mark points corresponding to the loop momentum are off. So you can always reduce it to those. But since these are suppressed by factors of epsilon in the degeneration limit, actually epsilon the higher powers. So they never make an appearance. That is the reason why I didn't want to say anything too specific about the non-supersymmetric theories, because that is not true there. So there's still more work that you need to do there to make sure that these non-physical poles never appear there.
Are there any more questions?
Yeah, you mentioned that you get results which are naturally written in this representation here that's related to the Q-cuts. And then, of course, often we're used to having a representation of the answers which is more like these pictures, local integrands, and you check that you get the results that agree with those. But I was wondering, so these new representations, are there some properties of the amplitudes that are more manifest than in these local pictures? Are there some intrinsic benefits, something directly starting from these moments?
So for me, BCJ and KLT relations are very manifest. So for example, the proof that KLT works at one loop for integrands, that just goes through as well. So properties like that, like things that you would say are fundamental for something like that, work very, very nicely in these. Obviously, if you want to... Okay, the other point that I want to make is that this is very much an object that just comes from, that is just a single object. It's not a sum over several terms. And so from that point of view, there's, at least for the non-supersymmetric theories, there's a very natural generalization to higher genus and higher loops that you can write down. There's still some work to be done on the supersymmetric ones. So in that sense, everything that you would say is sort of structural is slightly more manifest here. So you can, if you want to work out generalizations for something, this is a good object to start from. For actual calculations, there needs to be more work. I don't think sort of if you want something, an expressive calculation, usually you end up having to do something of the same again. So I don't know if for that it's more manifest. What I should say is that in general it's not the best method to just solve these equations, the scattering equations brute force. There's been very nice other methods. I don't know actually what. Mats Sogard and Yang Chang have very nice methods for getting around solving these completely. So maybe in combination with that, something might come out of it in the future.
Okay, so is there any more questions? Okay, this is the last one.
So you mentioned that basically to construct, to work from supergravity geometries, you let's say do the double copy, but in the inverse way, let's say. So you can explicitly get numerator factors in this way?
Well, if you worked it out, I assume you can. So this is more in spirit BCJ in the sense that the double copy works in the way that you have two factors that correspond to the spin 1, and you replace one by these Park-Taylor factors. The nicest way for getting these is actually doing a sort of current correlator and just picking out the pole structure that you want. I don't think there's been any work on explicitly constructing the numerators, but it might be possible. It would be interesting to check whether this works. Do you know if there's anything done at tree level even? I haven't seen any work that explicitly constructs the numerators from this, but
I think there is. The numerators you will get are those that have been computed in the superstring.
Okay, absolutely. From the superstring point of view, you're completely right, apologies. Yeah, from the string point of view, absolutely. There's been a lot of work in the string perspective that shows that these are the correct ones. And you're right, obviously, for genus 1, as long as you start from the torus expression, this should go through exactly the same way. I don't know if there's any, what I meant to say was that I don't know if there's anything new to be gained from these new representations here. Somehow, morally speaking, you probably land on the same numerators.
All right, let's thank Yvonne.